Hello, my name is Rachel Shaffer, and I'm a graduate student at Louisiana State University. Today, we're going to be talking about the low-lying states of boron 9 with the split pole spectrograph and SABRE. So the reason we're interested in boron 9 is because it is a very unstable isotope that's very difficult to study. And despite years and years and years of trying to classify its low-lying structure, there has been no definitive agreement as to the energy or width of this isotope's first excited state. We can look to the mirror isotope beryllium-9 to get an idea of where this state should be, but the fact that we're not seeing it there and that so many attempts have been made with such a wide variety of results is really concerning. So we are going to try to populate and classify this first excited state using boron 10 helium 3 alpha. We chose this reaction because the mirror reaction, boron 10 T alpha, successfully populates this mirror state in beryllium 9. Also, historically, there have been some results that agree within their error bars using this reaction. We performed our experiment at Florida State University using the John D. Fox accelerator. The tandem accelerator gave us a 7.5 MeV helium-3 beam, which bombarded a thin isotropically enriched boron 10 target. Then the alpha ejectiles from our helium-3 alpha reaction were momentum analyzed by the split pole spectrograph and deposited into the focal plane detector. This detector gives you a very accurate position measurement of your particles, which directly relates to the mass charge ratio and ultimately the energy of your ejectiles. The focal plane detector also tells you the energy lost while going through the detector, and then the residual energy is recorded by a scintillator at the back. Then the decay particles from the unstable boron 9 are going to be detected at backward angles with the silicon array for branching ratio experiments, or SABRE. Boron 9 ultimately decays into 2 alphas and a proton, either through proton emission beryllium 8 or alpha emission lithium 5. But in both cases, you ultimately end up with 2 alphas and a proton. Now, what we're looking for is all 3 decay particles in coincidence with our reaction's ejectile. A very important step in trying to find this is particle identification. So we can utilize the change in energy through the focal plane and the residual energy after it exits the focal plane to get distinct particle groups based on the mass and charge of the ejectiles. And we can gate only on the alphas and cut out all the other reactions that are happening that we don't necessarily care about at the moment. So that's what I'm doing here in this step. And by applying this gate, it greatly decreases our background and gives us some distinct peaks. So this purple spectra here, you have your boron 9 ground state, second excited state, and our area of interest. Purple spectra is all focal plane events. And then the subsequent spectra begin introducing different coincidence conditions. So you see a alpha ejectile in coincidence with 1, 2, or 3 SABRE hits. The fact that we still see such high count rates right in our area of interest at higher multiplicity conditions is very indicative of the first excited state being populated. So this analysis is still ongoing. These are very preliminary results I'm presenting here. So the next steps are going to be to get a very accurate SABRE energy calibration and then use the energy and momenta of the decay particles to reconstruct the original state that they decayed from. And then comparing our results with simulations to get a better understanding of what we're seeing. Finally, I would like to acknowledge Centaur and the NNSA for funding this work. and thank everybody who's helped me get my data and proceed with analyzing it, everyone that sat shifts. And thank you for listening. If you have any questions, feel free to email me.